Cool. All right. Well, great. Great of everyone to be here. Very, very full house. Very cool. I'm gonna have a bit of a more in-depth talk about DuckDB's execution model, and particularly our journey towards that execution model. So, like, because we have actually changed it in the middle of, like, after a few years, we were like, oh, what we did initially was wrong. Let's rewrite the whole thing. And that was kind of a gradual journey. So I want to kind of show where we started, why we changed, what we have now, and this is. There you go. Yeah, this thing is just new, so we're still getting used to it. Cool, yeah, so I will show some C++ code. I hope that doesn't terrify too many people here. I will explain it, don't worry. It's not that dangerous. It won't segfault on you. Yeah, cool. So push-based execution, that's the model we use. What model does Tiger Beetle use? Is pull-based, push-based, or neither? I'm kind of curious. Is there like a specific...
For queries?
For query, yeah, query execution.
We're sort of pool-based, like you give a buffer, pull some data in, ship it, come back for more.
All right.
Kind of like consuming a queue. Like
okay, I can show you what I mean by this. Maybe will kind of explain more like what I mean by this, essentially, right? There you go. Okay, so kind of just a high-level overview of execution that Hannes kind of already gave. A database system takes SQL and transforms it into query plans that somehow have to be executed, right? And the way it generally works is that you construct a query plan, which is a series of operators. It's kind of a tree. It's actually a DAG in DuckDB, but mostly it's a tree. And the way that works is that you just have like some operators that can be executed, like scans, where you actually go to disk, fetch data. You have things like joins, you have aggregates, and those operators, they all use different kind of like some mechanism of doing this execution, right? So if you do a hash join, the way a hash join works is that you construct a hash table and then you probe the hash table in order to find the matching join keys. If you do a hash group by, you construct a hash table. Again, we do a lot of hash tables to actually gather all of the unique keys, do the aggregation and such. And those operators, somehow you need to execute this tree, right? So that's kind of the fundamental question of query execution is how do you do this execution? And in database execution, there's kind of two main paradigms. You have pull-based and push-based execution model. And in a pull-based model, what happens is that each of the operators, they kind of go to their children, to their child operators, and they pull data like proactively, say, give me the data that I need, and then I will do the execution. And then the way that the execution works is that you have a tree, right? You pull from the root node, and then the data you get back is your query result. And each of the operators internally manages sort of the whole execution state. A push-based model is kind of the other way around, where instead of an operator itself pulling data from its children, there's some higher level data flow management, right? Like we call this the pipeline executors. They push data through the operators, essentially. And I'll show you some code examples. And, well, of course, this talk is called push-based execution. We didn't start off with push-based execution. We started off with pull-based execution. And like Hannes says, this is like pull-based execution. Maybe if you've looked at how other database engines do things, this is how most traditional database systems do things. So if you look at the Postgres source code, it's a very typical pull-based execution model. And in database literature, it's called the volcano model. And it was, I think, popularized by Guts Greve in like the 1980s, maybe the 70s, for SQL Server. And we do something a little bit, when we started, we did something a bit different. We did the vector volcano model, right? Because in the traditional system, like what Hannes mentioned, you pull rows, right? So you say to your child operator, give me a row. But because that doesn't really play nicely when you start processing large amounts of data, because you have to do like I pull a row, I pull a row, I pull a row, right? Like this function call overhead is very large. And if you have to say I pull a row a billion times, it tends to actually become like very costly, right? So what we had was not give me a row, it was give me a like batch of rows, right? Like give me a vector. And kind of the way this looks from a code perspective is that you have these operators, right? And each of these operators has a method called getChunk, right? So give me the data. That's the pull-based aspect of it. And the query, it starts by calling getChunk on the root node, right? You have a tree you call getChunk. And those nodes then recursively go back and they call getChunk on their children until you get to the scans, and the scans actually read data from disk, right? And kind of an example of how this would look like in like a projection, for example. If you don't know what a projection is, it's just like executing a bunch of expressions, right? So it's relatively straightforward. Like let's say I add a number to another number. I do like I plus 1, for example. That's a projection. The way you would implement a projection in a pull-based model is that you would say, okay, what does the projection do? Well, it needs to do its operation on something, right? Like if you do I plus 1, you need to get I from somewhere first. So it goes to its child and it says, okay, give me the data, right? And then if there's nothing left, right, the scan is exhausted, you just go back, and then you run the expression, you execute the expression and go into the result, and then basically bubble up the data to the roots, to the next operator in the chain. For a hash join, which is like a bit more complex, a hash join has two phases, right? You have the build phase and the probe phase. And in a hash join, what you would first do is you first build. So what you can do is you can check, hey, have I finished building? If not, then I will just go to like the build side and I will keep on pulling chunks and pushing them into my hash table, right? Like I will pull a chunk, build the hash table, pull a chunk, build the hash table. And when the hash table is like, when the right side is completely exhausted, right? Like there's no more data remaining, then I'm finished. I have my hash table, and then I can start pulling data from the probe side, and I can push, like I can actually start emitting results, right? So that's kind of like what that looks like. And this is, yeah, like kind of traditional Volcano model execution. And well, in this model, you can kind of see single-threaded execution is simple, right? Like you just execute it. Like single-threaded, it's easy. But yeah, in analytics, you kind of need multi-thread execution inside these queries, right? Because you have a query, it operates on 1 billion rows. A lot of it is already you need this stuff to be fast. A lot of it is often already in memory, right? Like so there's like the I/O can be a bottleneck, but often it isn't. Often your CPU is a bottleneck, and launching multiple threads can dramatically speed up the processing. Often like by a factor 10, factor 100, maybe even on some machines, right? And that makes a giant difference for users, like 2 orders of magnitude even. So how do you do this in this pull-based execution model? How do you do parallelism in this model? It's not very straightforward. And this has been thought of before, and there's some papers in the database literature about it. And it's essentially like, how do I bolt parallelism onto a single-threaded database? And again, this was done by DuckDB in SQL Server. A lot of the stuff, all the old database stuff was. And the solution is this exchange operator. And the way this works is that you take a query plan and you partition it. You basically start inserting these exchange operators inside the query plan. And what they essentially are is they're like repartitioning steps. So basically, if you think of this hash join, instead of building a single hash table, you would do a partitioning over like a radix key or something and create multiple different hash tables that are like completely independent from each other. And by doing this repartitioning, you can run each of these individual individual partitions independently. Because of course, if I read all my data, I can do the building on like the keys 1 to 10 separately from the keys 11 to 20 because they're guaranteed not to intersect, right? And that's kind of the way how they bolted query parallelism into SQL Server in, I don't know, 1995 or something. And it works, kind of. And with some queries, it's almost as fast as what we have done, particularly if you do like read a bunch of data and go into like one aggregate, right? Like if you have like a query like select sum from table without a grouping, right? Like a very simple aggregate works, but with more complex queries, which again, analytics is all about complex queries, it doesn't really work as nicely. And there's a bunch of problems with that. Well, first is the load imbalance issues. And that's because these exchange things like the parallelism, it's actually baked into the plan. So at planning time, you say, this is how many partitions I create, right? And it's just hard coded in there. You can't change it at runtime because all your stuff is already working. And you can't adapt this stuff either, right? So if you have any sort of imbalances in your keys, for example, like let's say I have twice as many keys in the range 1 to 10 as 11 to 20, my one thread is going to spend way more time than the other thread, and you can't deal with that because it's baked into the plan. In the worst case, you may have like one partition being empty and the other being full, and you basically revert back to single thread execution. Plan explosion is also a very fun one that comes from this, because you duplicate your plan by the number of threads. Nowadays, you can get machines with like 400 threads. You can get ginormous query plans with this. And the fun thing about that, well, fun, depends on whose side you're on. If you're on the programmer debugging this stuff, maybe not so much. The interesting thing about that is that database engines are generally not well equipped to deal with giant plans, because a lot of these optimizers, they're like quadratic in complexity, or sometimes even exponential in complexity of plan size. So we actually worked on a system that shall not be named that used this exchange operator. And one of the most frequent things they had to do was they had to optimize the optimizers, because they would run a machine with like 100 threads, generate a ginormous plan, and then their optimizer would suddenly take an hour when the actual query execution would take like 3 milliseconds. And that's not ideal, right? And there's also like added materialization costs, because you actually have to, like, essentially your parallelism model is built on this partitioning step, right? And that means that even if there is a more efficient way of doing things, you have to do this partitioning, and that ends up often being suboptimal, right? So it's not a very nice parallelism model, which is why we ended up not using it, right? We just ended up saying, okay, maybe this pool-based stuff is not for us. And this is something that Hannes has talked about previously, the morsel-driven parallelism. And that's kind of a more modern parallelism approach in analytical systems. Comes from a paper from the TUM guys. And the idea behind the morsel-driven parallelism is that instead of doing this sort of let's bolt query parallelism onto a system that's not parallel, we actually make the operators parallelism aware. We define like some interface to make the operators parallelism aware. And the core sort of like idea behind it is that you divide these queries into these pipelines that Hannes has showed, where within one pipeline data flows, and the pipelines internally have parallelism. There's also some other cool things there, like they have some NUMA awareness that they talk about, and they talk about like work stealing, where you adapt the sort of the like threads lazily gets blocks as they come in, which solves this sort of load imbalance issues. And yeah, it's much more promising. Okay, so I will again show the pipelines, kind of how it means. So if you didn't follow what Hans was saying, maybe this time we'll click. So essentially, the way these pipelines work is that you have this query plan that we saw before, right? So let's say I have a quite simple query where I have a hash join followed by a hash aggregate. Logically, you kind of have two stages in this query. You have a hash table built for the join, right? Like you have to build your hash table before you can start doing the join. And after the hash table is constructed, you have a second pipeline that then probes the hash table and computes the aggregate. And that's kind of what these pipelines are. They're like a partitioning of the query tree into like these like sequential things where you just have like a series of operators that can each be operated. And these pipelines, they have like a sink, right? They have a source of the data, which can be either a base table, but it can also be an intermediate, right? Because if you have an order by that can then stream into something else, or an aggregate that can stream into something else, like all these things are composable, right? Like you can have very large queries. So the source is just where the data comes from. You have some intermediate operators that are generally trivially parallelizable, right? Like a hash probe is trivially parallelizable because as long as the hash table is there, you don't need to do anything. You just look at the hash table. It's a read-only operation, right? Then you have the sinks, which again may have some form of contention or something that needs to be done to maintain this parallelism. Yeah, so the contention, it always happens at the endpoints, right? It's the source and the sinks. And kind of the base idea from like an API level perspective of how to design the system is that at the endpoints for source and sinks, you use parallelism-aware operators. So the interfaces, they are explicit about their parallelism. And the other operators like the hash join, the projection, the filters, they don't really need to know because they just do like some flat operation on their input data, and that there's no like contention that can ever happen inside of them. Yeah, so that's kind of the main, a big difference between this pull-based and push-based. like if you go back to the pool-based execution, you can see the data flow, right? It's entirely modeled within the operator, right? Like the operator itself is responsible for how data moves. So the hash join just says, hey, give me the data from my child, right? From the right child. Then give me the data from my left child. It's not managed in one like sort of central location. It's all like defined within the operator. And that makes it really hard to have any sort of like high level overview over a big query plan. And well, that's where our switch to push-based execution comes in, because basically this sort of like modern parallelism aware, parallelism execution paradigm we couldn't really do in pull-based very nicely. So yeah, what is push-based execution? Well, our previous model was push-based. Pull-based, push-based is the other way around, right? Like you push data into operators. So the operators themselves, they don't actually like touch their children directly. There's like this overarching executor that does that. And the push-based, it moves the data flow out of these operators, right? So the operators, they have no awareness of their own, like they don't directly manipulate the flow of data anymore. They only do what they say on the tin, essentially. And it's actually nicer in some sense from an implementation perspective, because it simplifies the implementation of the operators as well. But at a cost of like a reduction in flexibility, right? Like you can imagine in a pool-based model, an operator can do really crazy things with the flow of data. And in a push-based execution model, that's just not the case, because you have to define like one central location. This is how the data flows through my query plans. And then kind of the way this works is that instead of having this one single entry point, right? Like before we said, every operator has the get chunk interface and nothing else. We actually need to distinguish between these sort of stages in the pipeline. We need to say, oh, how does my sink look like? What does my operator look like? What does my source look like? And again, like a source emits data, operator processes data, sink consumes data. And this is kind of where the parallelism awareness comes in at a interface level. And if we look at the sink, like how that works is if you have a sink interface, you have both a global and a local state that the sink can define, together with like a combine and a finalize. And you can imagine, I mean, the global state obviously is like a shared sort of space where everyone, you need to be like aware that other threads may put data in there, right? And a local state is for whatever sort of thread local stuff you want to do, right? Like often if you build like a bigger hash table, you have some thread local hash tables first that are then synced or like flushed into the global hash table in order to do this efficiently. And then often you have to generate like a combine phase, which at the end you go like, okay, let's gather all this local state and actually make an operator. And there's finalize, where you go like, okay, now we want to actually complete the operator, right? Operator interface, very simple. It's not parallelism aware. You just take an input chunk and produce an output chunk, right? Like you can imagine in the projection, the way this would look is you get your input chunk, you run the expression, produce an output chunk. And the source interface, it's similar to the sink interface, but a bit simpler because you just get the get data, right? So you have these three different interfaces. And again, on the source, you have this global state that allows this sort of explicit parallelism within each of these operators. Cool. So that's, I think I have optimized out the slide that actually shows an example of this. I tried to make this short to fit into the 20 minutes, which has caused me to lose some slide. Yeah, so this is like a simple example of how a hash join would look. That's not it. That doesn't work. All right. Well, it disappeared again. This is a simple example of how a hash join, a probe would look, right? Like you just probe the input side and the output side. And you can see compared to the pool-based model, it's a lot simpler because the actual data flow has been handled outside of the operator, which makes the implementation easier. All right, so then we get into like how we get into how do you model all these operators, and for joins and how do you model this parallelism. And for things like joins and aggregates, it's somewhat straightforward often, but there are some edge cases that we immediately ran into when we were replacing our entire execution engine, as you might imagine. And that's why we came up with this concept of events as well as like an extra model on top of this. So an interesting one is unions. How do you execute unions? So do you all know what a union is in SQL? A union is essentially like I take one table and I take another table and I just glue them to each other. It's like a vertical join, right? Like a join combines the columns, a union combines the rows, essentially. It's how I kind of look at it. So if you have a union in SQL, in a pull-based model, it's very easy because in a pull-based model, you can do anything, right? Like it's the Wild West of query execution. So if you implement a union in a pull-based model, you just say, all right, first I get everything from the left side, and then when I'm done, I get everything from the right side, right? And because you have full control over the model, it's kind of easy. But then there's two questions. Like, of course, this is not parallel, right? Like, how do we do this parallel? And how do we do it push-based? And the way this works is that in a union actually causes you to have pipelines that have shared sinks. So if you think of a union that sits on top of some sink, like an aggregate node, right? Like here we have a sum, and we have two tables that feed into that aggregate. What ends up happening is that you have two pipelines, like we had before, but they have the same sink. And that actually works quite nicely because the sink is already sort of parallelism aware. But then you need some sort of communication between those different pipelines that basically say, okay, the pipeline is actually only finished when all the pipelines are finished. So it like creates some complication there. And kind of the way that we manage this is using these pipeline events. So what we did was, instead of having these pipelines themselves handle like saying like, okay, we have a pipeline that depends on another pipeline, we model the actual sort of stages of the pipeline as sort of independent things. So a pipeline has several like events. Basically, it has the execute event, where we actually run the data through the pipeline. It has the final, the finish event, where we say, okay, now we're done. We call the finalize method. And it has the complete event, where it starts like scheduling these dependencies, right? Because it basically says, okay, now we can move on to the next stage of the pipeline. And the way now we can actually model these unions using these pipeline events by creating these dependencies on this like slightly higher level. So we can say, okay, we have two pipelines, right? We have the left side and the right side that both flow into the same sink. And by decomposing this pipeline to these three different stages, we can say, okay, the left side and the right side, they kind of both go towards the same finalized because they flow into the same sink operator. And that allows us to do, well, basically do these unions and also nicely in parallel. And also, of course, it allows you to stack an arbitrary amount of unions because that also needs to work in like a nice way. Another one that's kind of interesting is full and right outer joins. I don't know if you guys have full right outer joins in Tiger Beetle. Okay, do you know what it is? Okay. Okay, so basically, let's have a normal join, like an inner join, right? It returns only the rows that have found a match. Then you have a left outer join, which means for every tuple on my left side, I always return a match, even though I haven't found any matching tuple on the right side, right? And that's, for one side, it's kind of easy because you can keep track of this only on the probe side, right? So you can say, in my probe, I look into the hash table. If I haven't found a match, I emit the tuple anyway, right? Like, it's somewhat easy. But a full outer join has this on both sides. So it says on my left side and on my right side, I have, if I don't have any matches, I need to emit tuples from essentially, possibly both of those sides. And that's somewhat of a complication because now you have a phase actually after the probing is done. Because essentially the way this would work is that you have a hash table, right? And within the hash table, you mark whether or not you found a match. And only after all the probing has completed can you actually start emitting these tuples, right? So you have this sort of third phase to a hash join if you have these kind of these types of joins. And that means that you need to scan the hash table after all the probing is finished. And this actually kind of nicely fits into this pipeline event model as well, because we can essentially say, okay, we have the execution phase, right? Like if we have a pipeline here that has a outer join, like full outer join, the execution phase scans from this table, goes into like, does the probing on the hash table, there's a projection, there's an aggregation, and then it can say, okay, after I'm done, I've probed everything, only then do I know which tuples haven't found a match in the right side, right? And then I can have a second, like another node that follows it up that says, okay, hold on, there may still be like nodes to process for this aggregate, right? So I can insert a second event which scans this hash table and feeds it into this aggregate. So that's also like nicely fits into this like decomposed pipeline model that allows you to do this. And of course, you can have like an arbitrary number of them together with unions as well, right? Like, it's all very nice. You can compose this, which means it works also if you have like 17 full outer joins, which sadly happens. Yeah, so outer joins. And another cool thing that this decomposed pipeline model allows you to do is that often if you have a sink, right, you may have an expensive finalized step. Like, for example, an order by, you may think of like doing some merge sorting or something like that, right? So you have some merge sorting involved. And those steps also need to be executed in parallel, and there may be arbitrarily many of them, because if you think of like sorting like runs, maybe you need to do like multiple stages of merge sorting. And that also fits nicely within this model, because in the finalized model, we can spawn new events that will then be inserted before we actually start executing dependencies on this event. So we can say, okay, my order by is done, but I actually still need to do some merging. But actually, I still need to do more merging afterwards. So that kind of like nicely fits into this this pipeline event model as well. Oh, that's all. Thanks for listening.